A standard coding portfolio is now a guaranteed ticket to the rejection pile. If you lack verifiable container orchestration abilities, automated screening systems will seamlessly filter you out before a hiring manager ever sees your application. Kubernetes mastery has become the ultimate career gatekeeper. This is exactly why the Ckad focuses heavily on application environment and configuration, which makes up 25% of your total score. It demands production-level survival. We are talking about implementing strict security contexts, designing intricate network policies, and deploying robust Helm charts, not just spinning up basic pods. In this video, we move beyond experimentation. I'll show you 5 high-stakes troubleshooting scenarios that separate the professionals from the beginners. Question number 1. A company is deploying a legacy Java application to Kubernetes. The application has a heavy initialization process and takes anywhere from 30 to 60 seconds to populate its in-memory cache before it can safely handle traffic. Once running, it occasionally suffers from deadlocks and needs to be restarted automatically. Which configuration provides the most resilient and responsive setup without causing premature restarts during initialization? Option A. Configure a liveness probe with an initial delay seconds of 60 and a readiness probe to check the cache endpoint. Option B. Configure a startup probe to check cache readiness, combined with a liveness probe for deadlocks and a readiness probe for endpoint traffic. Option C. Configure a readiness probe with an initial delay seconds of 60 and rely on Kubernetes default restart policies for the deadlocks. Option D. Configure only a liveness probe with a high failure threshold to account for both the slow startup and the deadlock scenarios. Option B is the only technically sound approach for this scenario. A startup probe is specifically designed for legacy or slow starting applications. It disables all other probes until it succeeds, completely protecting the slow initialization phase. Once the startup probe succeeds, the liveness probe takes over to monitor for deadlocks, restarting the pod if it fails, and the readiness probe ensures traffic is only routed when the cache is actually ready. Question No. 2. A development team is deploying a pod that must adhere to strict cluster security policies. The main application container must run as a non-root user, UID 1000. However, the application writes temporary data to a shared volume mounted at var data, and this data must be readable by a secondary sidecar container running under group ID 2000. How should the pod security be configured to achieve this natively in Kubernetes? Option A. Set run as user 1000 in the container's security context, and deploy an init container running as root to chown the volume to UID 1000 and GID 2000. Option B. Set run as user 1000 and run as group 2000 in the application container's security context. Option C. Add an annotation to the pod specification, security kubernetes.io volume ownership 1000 2000. Option D. Set run as user 1000 and FS group 2000 in the pod level pod security context. Option D leverages the FS group field in the pod level security context. When FS group is specified, Kubernetes automatically modifies the permissions and ownership of all files in the mounted volumes to be owned by that specific group ID, 2000 in this case, allowing any container in the pod that is part of that group to read, write the data. Question number 3. A microservices architecture has a front-end pod labeled app.awk frontend and a back-end pod labeled app.awk backend, both running in the production namespace. A default deny network policy is currently applied to the namespace, dropping all traffic. You need to create a new network policy that explicitly allows the front-end pod to communicate with the back-end pod on TCP port 8080. Which configuration correctly achieves this? Option A. Create a network policy with a pod selector matching app backend and an ingress rule allowing from a pod selector matching app frontend on port 8080. Option B. Create a network policy with a pod selector matching app frontend and an egress rule allowing to a pod selector matching app secure backend on port 8080. Option C. Create a network policy with a pod selector matching app search backend and an ingress rule allowing from a namespace selector matching app's front end on port 8080. Option D, create a network policy with a pod selector matching app front end, and an ingress rule allowing from a pod selector matching app backend on port 8080. Option A is correct because network policies are applied to the target pods, receiving the traffic using the main pod selector. By targeting the backend pod, you can define an ingress, incoming rule that explicitly allows traffic originating from pods matching the front-end label. Question number 4. You are executing a rolling update for a mission-critical deployment currently running 4 replicas. Business requirements dictate that during the deployment rollout, the application's capacity must never drop below the desired 4 replicas, but the cluster has enough resources to temporarily run up to 6 replicas. Which deployment strategy configuration guarantees these requirements? Option A, strategy, rolling update with max unavailable, 25%, and max surge, 50%. Option B, strategy, recreate with max surge, 2 and max unavailable, 0. Option C, strategy, rolling update with max unavailable, 0 and max surge, 2. Option D, strategy, rolling update with max unavailable, 2 and max surge, 0. Option C perfectly matches the constraints. Setting max unavailable. 0 ensures that Kubernetes will not terminate any old pods until new pods are fully ready, guaranteeing the replica count never drops below the desired 4. Setting max surge. 2 allows Kubernetes to spin up 2 additional new pods above the desired count, bringing the temporary total to 6 to speed up the rollout. Option A is a trap. 25% of 4 replicas is 1, meaning max unavailable would allow the deployment to drop to 3 running pods, violating the strict requirement to never drop below 4. Question no. 5. A pod runs 2 tightly coupled containers, a web application and a log forwarding agent. The web application generates access logs to a local directory, and the log forwarding agent must continuously tail these files and ship them to an external SIEM. If the pod crashes, is evicted, or is deliberately deleted, the local log files should be immediately and permanently discarded to save disk space. Which volume configuration is the most appropriate for this architecture? Option A, mount a persistent volume claim, PVC, configured with a retain reclaim policy to both containers. Option B, mount an empty dir volume to both the web application and the log forwarding agent containers. Option C, mount a host path volume to both containers, pointing to var log pods on the worker node. Option D, mount a config map volume to both containers to act as a shared memory buffer. Option B is the correct choice. An empty dir volume is created when a pod is assigned to a node, and it exists exactly as long as that pod is running. Containers within the same pod can read and write the same files in the empty dir volume, making it the perfect solution for tightly coupled sidecar patterns, like a log forwarder. When the pod is removed or evicted, the empty dir data is deleted permanently, satisfying the requirement. For complete exam preparation, visit p2pexams.com, where you'll find high-quality practice questions, exam simulations, and expert-designed study materials to help you pass with confidence.